are almost there, so this is the last talk today, so I hope you can enjoy it. Yeah, I'm Ruiqi from Google DeepMind, so legacy Google Brain team. So today I'm going to talk about understanding diffusion model objectives from the perspective of ELBOs. So first of all, I would like to give a big shout to my amazing colleagues and collaborators who made part of the works covering this talk to be there. And part of the slides are taken from the tutorial we made in CVPR 2022. So feel free to check the tutorial if you want to learn more basic knowledge about diffusion models. So over the past 2 years, we can see it's really, someone said it's really about the years of generative modeling because we see like great explosion about large language models. And meanwhile, from the visual side, we can see a lot of great, amazing projects about like image generation, video generation, as well as 3D generation. And fortunately, some are done by Google, but some are done by the external community. And if we dig out the underlying models of those great projects, we can see like many of them are actually powered by these diffusion models. And with diffusion models, we are able to generate, say, AI art with Midjourney V5. And as Jeff also mentioned, it's also possible to generate even AI movie by combining different generative models. Say this is like a generation combining Midjourney image generation, runway video generation, as well as Trinity audio generation. So all of them are powered by diffusion models. And of course, you can make this whole process to be even more automatic by, say, recruiting a large language model as the AI agent. And of course, diffusion model has been extremely powerful for solving inverse problems, for example, super resolution, like image restoration, for example, colorization in painting and restoration, as well as outfilling. So if we take a look at the landscape of deep generative models, we have like a long history of developing different types of generative models. For example, this generative adversarial networks has been dominating the whole field for like almost like 5 years, I would say. And we have other type of generative models, for example, variational autoencoders, energy-based models, autoregressive models, which is a leading model in language, but less leading, I would say, in the vision domain, and as well as normalizing flows. And we have these diffusion models. So if we take a look at the training objective used for training those different types of generative models, we can see most of them are likelihood-based models, meaning that if we want to learn the model parameters, we're basically using maximum likelihood or the variant of maximum likelihood, which is called evidence lower bound. However, if we take a look at the training objective of diffusion models, it doesn't necessarily correspond to the ELBO, although like it's possible that we optimize diffusion models towards the ELBO. But the state-of-the-art diffusion models actually use something slightly different. It's actually a reweighted version of the ELBO. So that's the motivation of this talk. So we have already seen that diffusion models are extremely successful in both like image, video, as well as sound generation. However, the use training objectives giving the best perceptual quality are not actually likelihood or the ELBO. So that raised like a very fundamental question: is the log likelihood not trustworthy anymore if our really main motivation is to generate good-looking samples? And that also raised another question. So how can we do apple-to-apple comparison of diffusion models with other type of generative models that actually trend towards maximizing likelihood? So this is an overview of the content that's going to be covered in this talk. So first, I will briefly recap the formulation of discrete time ELBO developed by the DDPM paper. This is just like slightly different interpretation of diffusion models than the score matching framework introduced by Jeff in the morning. And then we will see how we can extend this discrete time ELBO to continuous time ELBO case. And finally, we will draw connection between the currently used diffusion model objectives in the literature with the continuous time ELBO. And if time permits, I will briefly mention how we can do fast sampling of diffusion models by progressive distillation. So let's start from the discrete time ELBO. So this is like, we already know a lot about this. So diffusion models contain two processes. The forward process is just gradually adding noise, and it's usually fixed. And the model we need to learn happens within this reverse denoising process, where we learn a denoising distribution to iteratively denoise from a pure white noise image to the clean sample. And for the forward diffusion process, we can define the stepwise denoising process, which is categorized by this QXT given XT minus 1. And this gives us a joint distribution of this forward diffusion process. And if we compare, we want to draw analogous to from diffusion models to variational autoencoders. So this process is actually pretty similar to the inference model in the hierarchical VAEs, where we start from a observed data and we gradually derive the latent variables in a hierarchical way. And similarly, we can have this reverse denoising process. Again, we can define this denoising distribution, which characterize the probability of xt minus 1 given xt, which is sample at a higher noise level. And we can show that if the noise added at each step is small enough, then this distribution can be approximated by a Gaussian distribution. And here, the mean of the Gaussian is where we want to learn, and it's usually categorized by a trainable network. And because this mean takes the noisy sample xt as input and will output something of the same dimension of xt, it's usually parameterized by a U-net. And this gives us a joint distribution of this reverse denoising process. And this process actually is pretty similar to the generative model part of a variational autoencoder, or more precisely a hierarchical variational autoencoder, where we start from a pure white noise latent variable and gradually generate the latent variables layer by layer until we generate the clean sample. So now we are at the right time to define the ELBO, or the negative ELBO of this model. To be more specific, if we treat the reverse process as a generative model, we can derive, the left-hand side is the negative log likelihood, but we cannot compute it exactly. So therefore, we introduce this inference network distribution, and then it becomes a negative log ratio between our generative model and the inference distribution. And we take expectation over the training data as well as this inference model. So this is essentially the same ELBO that we use in variational autoencoder. And in these two works, actually show that this ELBO can be further decomposed into 3 terms, and this formulation can have a smaller variance compared to the original ELBO formulation. If we take a closer look at this objective, the first term corresponds to the distribution of the noisiest image and the prior distribution of x big T, which is essentially Gaussian distribution. So if we assume that our forward process goes to something that is close enough to the pure Gaussian distribution, then we can basically ignore the first term. And the last term is basically the log probability of the clean sample given the first noisy sample. So this is usually parameterized or predefined by something that doesn't contain learnable parameters. So the only thing we need to care about is the second term. And the second term is actually the KL divergence between QXT minus 1 given XT, which is the sample of a higher noise level, and the clean sample, which is X0. And with the denoising distribution modeled by our model, which is P theta XT minus 1 given XT. And the nice thing is, like, for this Q distribution, is again, we can show it is a Gaussian with tractable posterior distribution. And here, this mean of this distribution looks like a monster, but it's actually just a simple linear combination of the clean sample X0 and the current noisy sample XT. And because we know like both this Q distribution and this P theta are Gaussian, we can derive the formulation or the trackable formulation of this KL divergence term, which is in the form of the L2 distance between the posterior mean of the Q distribution and the predicted mean of the denoising distribution, which is this mu theta. And then the next question is, how should we parameterize our network for this mu theta output? So in this DDPM paper, they observed that we can write the posterior mean of this Q distribution as a linear combination of the current noisy sample XT and the ipsum, which is the noise added to the clean sample in order to generate the noisy sample XT. So therefore, they propose to parameterize the mu theta network in a formulation pretty similar to the posterior mean of this Q distribution. To be more specific, the only difference here is that for the denoising distribution, we don't know the ground truth X0, so which means we don't know the ground truth noise added to the clean sample. So we just replace the ground truth noise here with a noise prediction network ipsum theta. So after we do this reparameterization, we can see the KL is in a very simple form. So it's basically just the L2 distance between the ground truth noise added to the clean sample and the predicted noise by our network. And here we have weighting functions, or like a weighting term in front of this L2 distance. Okay, so this is our ELBO, but in the DDPM, they observed that the best sample quality actually derived by the following L-simple objective, where we simply drop this weighting term in front of this L2 reconstruction loss. And actually, this difference is big. So if you use the original ELBO, you get much worse sample quality. So this is really interesting. So why this L-simple is like a little bit far away from the ELBO actually work better than the variational upper bound or the negative ELBO? So this is the main question we want to address. A little bit more connection to VAE. So diffusion model can be actually considered a special form of hierarchical VAEs, with the difference is that the inference model is fixed, and the latent variables has to be the same dimension as our data input. And the ELBO is actually decomposed into the loss term of each time step, so that when we compute the ELBO, we don't need to go through the whole denoising and reverse process. We can sample certain time steps, which make it faster to train and can make the model to be very deep. Actually, in the continuous time case, it corresponds to an infinitely deep variational autoencoder. And the last difference is that the model is not trained with the ELBO, it's trained with some reweighted version of ELBO. Okay, let's come to the continuous time ELBO case. So we want to do a little bit change of notation. So we assume the clean sample is represented by X, and all the noisy samples represent them by Z to draw a more explicit connection with variational autoencoder. And we change the time step from 1 to big T to this 0 to 1. And the time steps is given by this delta T. And we design this forward process by assuming this marginal distribution of ZT given X first, and derive this stepwise diffusion process correspondingly. And if we let delta T goes to 0, this gives us this continuous time diffusion model. To be more specific, it defines a joint distribution from Z0 to Z1, and there can be infinite number of latent variables for this joint distribution. And it can also be categorized by a stochastic differential equation, as Jeff also mentioned in the morning. And similarly, for the reverse process, we have this denoising distribution for arbitrary ZS given ZT as long as S is smaller than T. And let delta T goes to 0. We also have this joint distribution of this reverse process. Again, it can be a joint distribution of infinite number of latent variables. And then we are ready to define the ELBO in this continuous time case. So if we again assume like the forward process can denoise to something close enough to pure Gaussian distribution, then we only have two terms in this ELBO. One is this reconstruction loss, which is the log probability of the clean sample given the first noisy sample, and this diffusion loss. And remember, like in the discrete time case, we have a giant weighting term in front of this L2 reconstruction loss. But in the continuous time case, it can be actually expressed in a much simpler form. Basically, we have this weighting in this brown color, and we introduce a new notation, which is this log signal to noise ratio of the current time step. Basically, it defines the ratio of the information and the noise at the current time step. And we can see the weighting in front of this L2 distance is simply the time derivative of this log signal to noise ratio and takes the negative of it. And I would like to talk a little bit more about this noise schedule. This actually defines a similarly quite important design choice in diffusion models, and people have proposed different design choices for this noise schedule in the literature. And it's usually called noise schedule, which corresponds to the mapping from the time step t to the log signal to noise ratio lambda. And another interpretation, and this function, it usually assumed to be strictly monotonically decreasing, which means as t goes larger, we have less signal but higher noise. And it's invertible because it's strictly monotonically decreasing. And another interpretation of it is that if we assume t is uniformly sampled, and then this actually defines a distribution over the lambda, the log signal to noise ratio. So actually in some framework of diffusion models, we can completely drop the concept of time steps, but we only use this lambda to define our denoising and reverse process. So we don't need to necessarily have an explicit concept of time. And here we plot certain noise schedules used in the literature. To be more specific, this blue curve is called cosine schedule, which is the most commonly used noise schedule for pixel-space diffusion models. And we also have this EDM, which is the improved version of it. And we can, so the left figure draws the mapping from T to lambda, and the right figure shows the probability of lambda corresponding to the noise schedule on the left figure. So we can see that for the training noise schedule, usually people use a bell-shaped one, meaning that we want to put more emphasis or want to sample more frequently in the middle region of this low signal-to-noise ratio regime. But it's worthwhile to mention that we can use a totally different sampling noise schedule. That's how this EDM paper also did. So we can use, different design choices. Okay, so if this noise schedule sounds important to our objective, after we have this continuous time ELBO, it's actually possible that we optimize this noise schedule together with our diffusion model, the parameters of our diffusion models. However, in our early trials, this doesn't lead to better performance for either likelihood estimation or perceptual quality. So we're wondering why this doesn't help. So we actually see that the ELBO is actually invariant to the noise schedule. To be more specific, this is our ELBO. And this ELBO can be written as the integration over the time t. And if we do a change of variable, we change this dt to d lambda, we can see that this brown term actually disappeared. And this ending training objective is actually irrelevant of the probability of lambda. So actually, this ELBO only related to the endpoints of this noise schedule, which means that we don't need to actually worry a lot for the schedule in between the endpoints if we only care about ELBO or weighted ELBO. Okay, and in this variational diffusion model work, they actually show that if we optimize diffusion models towards this continuous time ELBO, it can actually lead to the state-of-the-art likelihood estimation generation results. So this blue tube is the one generated by, achieved by diffusion models, and it actually improves a lot based on the other autoregressive baseline. So autoregressive models dominate this likelihood estimation benchmark also for a lot of years. But what we care about is quality, the sample quality. They actually are trained with some reweighted version of this likelihood or of this ELBO, but not necessarily exactly the ELBO. So if we really care about perceptual quality, is the log likelihood objective wrong in that case? So that comes to our latest work where we connecting the diffusion model objectives to the ELBO. To be more specific, let's first list several commonly used diffusion objectives in the literature. The first one is from the framework of denoising score matching. So we have this L2 distance between the predicted score and the ground truth conditional score. And we can have a weighting term in front of it. And usually this is like heuristically tuned. We can have this very commonly used noise prediction or L-simple training objective, which essentially ignore any weighting terms in front of this L2 distance between this predicted noise and the ground truth noise added to the sample. And finally, we have this ELBO, which corresponds to having an extra term in front of this L-simple objective. So we can summarize all the existing training objectives in the literature by the following weighted loss, where we keep the ELBO formulation and we add a weighting term in front of it, so which is in this green color. And this W can be either the function of the lambda or the function of T, because there is a bijection between lambda and T. So for ELBO, we know like W lambda equals to 1, and it's best for likelihood estimation. And for example, for noise prediction loss, this W lambda equals to something that can get the brown term to be canceled out. And this is like very great for generating plausible samples. And we also did a great summarization about almost all the training objectives we can find in the literature. And we listed the corresponding formulation here. And one interesting we found is that if we make the plot of those weighting functions, so we take the W lambda as the y-axis and the lambda as the x-axis, we can group the existing weighting functions into two plots. The left one shows the non-monotonic weighting functions, meaning that like most of them are in this bell shape, meaning that again we put more emphasis on the middle region of this lambda. And there are another group of weighting functions which is monotonically decreasing as a function of lambda. So here we come to our main finding of this paper. So if we have some mild assumption of this weighting function, which means like we assume this weighting functions is monotonically decreasing over lambda or monotonically increasing over t, then we can show that actually the weighted diffusion training objective is equivalent to the ELBO, but with simple data augmentation. So let's dive into details about this main finding. So first of all, I want to define a notation which is a negative ELBO of noisy data. To be more specific, we assume we have a partial diffusion process where from the clean sample X, we directly jump to a ZT, for example. This T is a randomly sampled time step. And after that, we begin to build our diffusion models. So we have this partial forward diffusion process, as well as this partial backward diffusion process, which is the joint distribution QZT to 1 given X. And the partial backward diffusion process is just a joint distribution from ZT to Z1. And then we define the KL divergence between this partial forward diffusion process and the partial backward diffusion process. And we denote it as LTX, indicating that it is something starting from time step t and with clean sample x. And we can actually show that this L corresponds to the negative ELBO of the noisy data at time step t. To be more specific, we can derive that this KL divergence is larger or equal or larger than the marginal distribution QZT given x, and the KL divergence between that one and the model marginal distribution PZT. And this actually corresponds to the negative log likelihood of the noisy data at time step t. Okay, so after we have this notation, we will have our first statement. So the weighted loss can be actually seen as a weighted integral of ELBOs. To be more specific, recall this is our weighted training objective. And we can actually show the time derivative of this LTX we just defined is given by this formulation. So it equals to 1/2 times the d lambda over dt times the expected L2 distance between the ground truth noise and the predicted noise. So we can actually plug in this formulation to the weighted loss. And then the weighted loss can be rewritten in a very simple form. So it's an integration over time and negative time derivative of this L times the weighting function W lambda. And if we further do an integration by part operation, we can actually move the time derivative from this L to this weighting function omega or W. So here we can see that this weighted loss is actually an integration over T, and this is like the weighting term, and this L is the ELBO of some noisy data. And we can merge this guy, which is the L0x, which is a full ELBO, to the first term, actually. So this gives us a conclusion that weighted loss is actually weighted integral of ELBOs at different noise levels. And then the second statement we made is like, if we have some mild assumption of this weighting function, this weighted loss can be understood as ELBO with data augmentation. To be more specific, so this is our weighted loss. So if we assume that W lambda is monotonically increasing in T, and also it is normalized such that W lambda 1 equals to 1, then this dW dt actually give us a probability distribution. So this W lambda T is the distribution, the cumulative density function of this distribution. So we can write this weighted loss as an expectation of those noisy ELBOs, and the distribution of this T is determined by this W lambda T. So this is our second statement. So this weighted loss equals to ELBO, but with simple data augmentation, namely Gaussian noise perturbation. And this weighting function controls the distribution of this data augmentation. Okay, so this is like the main results. So we are curious, like, what's the intuition that for best perceptual quality we need to do such kind of data augmentation, right? So let's take a look about what happens to an image when we do this Gaussian noise perturbation augmentation. So suppose we have x0 as our clean data, and then we add some certain amount of noise to reach this xt. And we can encode this linear transformation in the Fourier space, so which means like the Fourier component of our clean sample is also perturbed in the Fourier space. And assume this is like the distribution of the magnitude of different Fourier components. And as we can see, when we have a small noise level, then if we compare the magnitude of the Fourier components of the data versus like the magnitude of the Fourier components of the purely white noise, which is this epsilon, we can see the magnitude is more similar to each other at high frequency regions. But the low frequency components of the data has higher magnitude at the early stage of the denoising process or the Gaussian noise perturbation process. However, as we add more and more noise, then the low frequency components become to be more perturbed with the pure white noise at that stage. So as we can see, as noise gradually increases, the high frequency components actually is perturbed faster compared to those low frequency content. Therefore, if we take a look at this Gaussian noise perturbation process, if we add a small amount of noise to the data, then almost all the components are still retained, so that the model is still required to capture all the details, including the low frequency content and as well as the high frequency content. As we're adding more and more noise to it, then if we build the model at this noise level, which means that we build the ELBO at this for this noisy data, then it's specialized to capture only the low frequency content or high level content of the image. So that explains the motivation of doing data augmentation if we really care about perceptual quality. Because that if we do this data augmentation, the model is forced to put more emphasis on modeling the low frequency content. And we know like low frequency content sometimes is more important to human perception, while for some low level details or high frequency content, they are actually invisible to human perception. And we can also draw another connection with low bit training. So this is another technique widely used in previous literature. For example, for flow-based generative modeling, instead of training on the full 8-bit data, which is the full bit for an image data, sometimes you will reduce the number of bits to, say, 5-bit, and it usually leads to better perceptual quality. And the low bit data is usually obtained by simply adding uniform noise, and in certain cases, it's really similar to adding Gaussian noise. And we want to draw a connection between the low bit training. So again, this is our weighted loss. And to do a change of variable, we can change from dt to d lambda again. So this is like the weighted integral if we integrate over d lambda. OK, so after we have this formulation, we can think about a toy example where we assume our NB data is very simple. It's just like uniformly distributed over 2 to the power n possible pixel values. So if we change the number of n, we change the bit precision of this training data, which is pretty simple. And under this toy example case, we actually know the optimal model for this PZT, which is given by a mixture of Gaussian, and each Gaussian component is a Gaussian centered around each possible pixel value of the 2 to the n power pixel values. And under this case, we can actually compute the derivative of this L lambda x over d lambda accurately and explicitly. So we can draw a curve. So each curve corresponds to this d lambda over the value of lambda. And we can draw multiple curves for different number of bits of data represent different precision. And more interestingly, we can take a difference between adjacent curves. For example, we can take the difference between this orange curve and with 1 bit lower, which is this blue curve. So this gives us the difference between each bit of bit data. And this gives us the intuition about if we want to gradually add more bits to our training data, what would be the contribution of each added bit to this DLD lambda term. And we can see that as we increase from bit 1 to bit 8, so meaning like we gradually add bit 1 by 1, then the contribution gradually shifts from low signal to noise ratio region to high signal to noise ratio region. So this again aligns us analysis about Fourier analysis, which means that if we really want to compress our data to very low bit, then the content remaining is all about like low signal to noise ratio regions. And as we continuously add more text details to the data, then we gradually go to high signal to noise ratio region. And now it becomes more clearly about what the weighting function means. So if we combine those two, we put those two figures together, we can see that if we use a monotonic weighting function, it essentially means that we are trying to shut down certain bits of the data. And actually, if we care about, like, say, training with 5-bit data, it's actually pretty similar to that we train on an 8-bit data, but we design a sigmoidal weighting function. For example, this purple curve, which has a sudden drop in certain region. For example, it will be lambda belong to 7.5 to 10. So this means like if we have the weighting function for our diffusion models, then the low bit training can be considered as a special case of designing a certain type of weighting function. Okay, so with this theoretical understanding, we are hoping to give some insight about for practitioners when you define your own diffusion models. To be more specific, we designed two new monotonic weighting functions. The first one is given by the intuition drawn from low bit training. So we can design a sigmoidal weighting functions with different shifting and scaling term to be hyperparameters. It actually can be considered as a smooth version of step function. If you use the step function, it essentially means like you only train on certain noise level. And the second one, we name it as EDM monotonic. The motivation is that we found a weighting used by a state-of-the-art diffusion model, which is this EDM paper, is a non-monotonic weighting function. But we can make it monotonic by setting the weighting on the left-hand side of the maximum value of the argmax value of lambda to be always equal to the W max. So originally it's like a bell shape, so we just put the left-hand side of it to be constant as W max. Okay, we will see the empirical results later, but before that, I'm going to revisit the invariance to the noise schedule, so we can actually show that the weighted training objective is also irrelevant to the noise schedule design. So it only related to the endpoints of these noise schedules. However, it still affects the variance of the Monte Carlo estimator because this integration cannot be computed in a trackable form, so we had to sample Monte Carlo samples to estimate it. To be more specific, this noise schedule can be viewed as an important sampling distribution if we write the weighted loss in the following form. So actually, based on this insight, we propose to have an adaptive noise schedule where through the training process, we just make this P lambda to be approximately proportional to the weighted loss. So in this way, we can make sure the loss is spread evenly over time. And empirically, we'll find it works pretty well, and it also speeds up the optimization process. Okay, so we can see some experimental results. So on the 64 by 64 ImageNet, we did an extensive ablation study over the several important design choices of diffusion models, namely the model parameterization, which means like what kind of output we assume our UNet is, and then the noise schedules, the weighting functions, as well as what kind of sampler we want to use. And we have several conclusions based on these experiments. So first, we can make any existing non-monotonic weighting function in the literature where we take this EDM as an example to be monotonic, and this won't lead to any loss of image quality. And sometimes it also leads to better image quality. And second is that with our newly proposed weighting functions, we can achieve state-of-the-art results. And third is that we compare the original noise schedule used by the baseline methods versus like the adaptive noise schedule we proposed. And it performs equally well for the ending results and also converges faster. And last, like all the conclusion above holds agnostic to certain model parameterization or sampler we use. And later on, we also generalized to more challenging tasks, for example, high-res generation, image generation. And we're using a backbone model called Simple Diffusion, developed also by my colleagues. Can be considered as a state-of-the-art high-res image generation model. And the only thing we change is that we change the weighting function to our proposed ones, and also we use the adaptive noise schedule. And we also achieve state-of-the-art results for all these challenging benchmark. And we can see that compared to the simple diffusion, which is our backbone model, we achieve great improvement performance compared to their models. So it's actually means that our methods can be actually easily applicable to any other existing diffusion models. It's literally just one linear change for the weighting function and for the noise schedule. And we show some empirical results like the samples generated from our models. Okay, so since we still have some time, I want to briefly talk about distillation of diffusion models inspired by the earlier talks, like people are complaining about like the slow sampling of diffusion models. So basically, we want to solve the slow sampling problem of diffusion models by running distillation. To be more specific, we assume that we already have a deterministic ODE sampler, for example, a DDIM sampler from a pre-trained diffusion model. And then we will name the original diffusion model as a teacher model. And then we will start by having a student model, which which is initialized from the teacher model. And during this sampling process, at each stage, we just want the student model to use one sampling step to reproduce the output from the teacher model using two sampling steps. So after the training of each stage, we will halve the number of sampling steps. And then the student model will become the new teacher model. And then we will repeat this process so that we repeatedly halving the number of sampling steps until we reach the desired number of sampling steps, for example, one step. And actually, if we take a look at the implementation, it's very similar to the original diffusion model training. The only difference is highlighted in green color. So first, instead of having like a training data, we have a trainable pre-trained teacher model. And then we initialize the student from the teacher model. And the difference is here. So originally, we have the target to be the ground truth noise added to the clean sample. But now, the target becomes the teacher model output instead of the ground truth sample or the ground truth noise added to the clean sample. And the training objectives is essentially the same. We just use L2 distance between either the predicted noise or the predicted clean sample. And we have a weighting function in front of it, which we can use our newly proposed weighting functions. And we repeat this process. And with this approach, we have applied it to a lot of state-of-the-art diffusion methods. And we have shown that it works with classified free guidance. And it also works with stochastic sampler, which I don't have time to cover in this talk maybe. So it not necessarily can only work with DDIM sampler. It can also work with DDPIM sampler or like more advanced higher order samplers. And we apply it to different large-scale diffusion models, include text-to-image, text-to-video models, as well as some models solving inverse problems. And we also apply it to latent diffusion models, or more specifically, stable diffusion. And for all those models, we will be able to reduce the number of sampling steps to 1 to 4 sampling steps. So right sample shows all the samples from the distilled stable diffusion. So the top left is with 1 sampling steps. And we also show some 2 sampling steps results and 4 sampling step results. And we also show that we can distill, say, an image imprinting model or an image-to-image translation model just by applying the similar approach on top of it. Okay, so that mainly ends the major part of my talk. So some takeaways. So for theory enthusiasts, so we have shown that state-of-the-art diffusion objectives can be actually understood as ELBO with simple data augmentation. So thankfully, like ELBO is still compatible with sample quality and good-looking sample generation. And for practitioners, we show that diffusion model performance is irrelevant to the choice of noise schedules. So you can simply use, say, our adaptive noise schedules, and it should work with your own diffusion models. And third is like we propose some new weighting functions that works great for pixel space diffusion models, and you're very welcome to try on your own diffusion models. And we can make sampling to be faster by progressive distillation. And the results we have seen also have a open question we want to answer in the future. That is, if we want to really do apple-to-apple comparison to diffusion models with the other type of models, for example, autoregressive models, can we compare them, just use exactly the same objective as we just put theoretical understanding to, so that we have a better understanding about like really which model class performs better under the same objective or under the same data augmentation. Okay, a slightly pitch. So if you want to learn more details about diffusion models, welcome to check our CPR tutorial. And if you happen to come to NeurIPS this year, we have a workshop about diffusion models with a great list of speakers and panelists. And we also have a tutorial at NeurIPS this year about latent diffusion models. And finally, our team is hiring student researchers and interns, so feel free to reach out if you're interested. Okay, thanks for attending this talk.
Okay, Hurik.
Thanks for a nice talk. I had one question. So if we think in terms of the state-of-the-art diffusion models, right? There's a weighting that you said based on ELBO. So, and then you gave a very nice interpretation. But how would loss function, in terms of importance, relate, say, amount of training time you do, or amount of training data you drop on the training of the diffusion model, like which are considerations to get the state-of-the-art performance? So what are the relative importances of training time, training data, and the loss function?
Yeah. You made a great point. So I would say like all of them are super important, and especially for the data front. So it becomes more and more important nowadays. Sometimes it's not necessarily like the more data you have, the better results you can get. It's almost about like the balance between the amount of data you use and the quality of the data. So a commonly used strategy is like you first train your model on a huge amount of data, but might be lower quality, but then you fine-tune your model on a small subset of high quality data. So empirically that matters a lot, especially for if you check the, for example, Stable Diffusion Midjourney V5 and other open projects, for example, Ideogram. All of them are great text-to-image generation models, but they can be specialized to different regions. For example, Ideogram works better for rendering text to your samples, and Midjourney is better than artistical style generation. So I think all those things are kind of related to what kind of training data you use, of course. I think the weighting function is also important because it, like empirically, we see some great improvements on top of that. And also like a better noise schedule can give us like more training efficiency, so we can save some compute and training for shorter time. Yeah, I definitely feel like it's really a combination of modeling and also some engineering effort.
Any other questions? I'm going to go here, and then I'm going to go there, and then there.
Hi, Dr. Thanks for your presentation. There's always a question that's confused during my research. It's a very high-level question. Is there any intuition why the distillation could accelerate the diffusion model? Sometimes I think even the student model could even outperform the teacher model. Is there any intuition behind that?
Yeah, that's a great question. So speaking of the outperform thing, I think that's related to one technical details about distillation algorithm. So when we distill a sampler with classifier-free guidance, we will make the student model to be conditional on the weight, the strength of the CFG. which means like after distillation, we want our student model to support sampling with different value of classifier-free guidance. So this actually acts a little bit similar to data augmentation. So we train our model to perform multiple tasks with a conditioning of the guidance weight. So this also like helps the image performance. And speaking of why distillation can work so well, I think so after distillation, it's not relevant to the diffusion framework at all. So you cannot think it as a score function at all. So basically, it's really just like, okay, we have a deterministic ODE path, for example, and then we just want a neural network to reproduce the ODE path given the starting noise and the ending clean sample. And the hypothesis is like the UNet, if you really build it as a deep UNet, it has such kind of capacity to model this kind of deterministic sampling path. Yeah.
Hi, thanks for your talk. I was also going to ask about distillation. What's the time complexity of the progressive distillation algorithm, and how computationally expensive is it compared to the standard diffusion model?
Yeah, that's a great question. So empirically, we found that, so at the first glance, it sounds to be expensive, right? Because we need to repeat it for multiple stages. But actually, for each stage, the task is relatively simple because the student model is already initialized from the teacher model. So if you only wanted to reproduce one step of teacher model, it already achieved that, right? So now you just have a little bit add-on. So you, instead of want to reproduce one sampling step, you wanted to reproduce two sampling steps. So it's kind of a relatively simple task for the student model. So empirically, we found that the total number of sampling steps you need for running a progressive distillation, if you add all the iterations together, it's still smaller than the number of iterations you need to train the original diffusion models. And you might want to spend more time at the later stage. For example, we need to spend more time when we reduce from 4 sampling steps to 2 sampling steps. Again, because the task is becoming more and more difficult because the step size you want it to be covered becomes larger and larger per stage.
Hi, thank you for your very insightful talk. I'm wondering, many of your interpretations of the ELBO is based on monotonic weighting function. If the weighting is not monotonic, does your interpretation still hold? And do they imply some emphasis on maybe not low frequency signal, but middle frequency signals, something like that?
Yeah, that's a great question. So actually, we have 2 statements. So the first one is, let me find the right slide. So we have 2 statements. One is that the weighted loss is a weighted integral of ELBOs. So this conclusion doesn't necessarily require the weighting function to be monotonic. Only when that you want to think about it as the data augmentation, then there you want your weighting function to be monotonic. So I think the intuition about, say, low bit, the connection between this weighted objective with, say, low bit training still holds, even if your weighting function is not monotonic. So basically, if you compare this weighting function with the low bit training, so if you have a non-monotonic weighting function, it means like you not necessarily want to shut down the bits on the right. You might also want to shut down certain bits on the left. Yeah.
I'm going to go there, and then we'll go there.
Thank you for your talk. So just one of small comments. So looks like the accelerating sampling, the idea looks like very similar to the philosophy in multi-grid. Like we solve the problem in course first, then we refine. Then my general question, do you think like the philosophy in multi-grid methods maybe can help to accelerate the sampling? Like your opinion?
Definitely. Yeah, I think there's already some works pretty relevant to your ideas in the literature. For example, there's a subspace diffusion models where they try to repeat downsampling the image when you, and then you only diffuse the residual with a relatively short diffusion process, and you diffuse the low-level contents with a longer diffusion process. So I think that's definitely something that's worthwhile to explore, especially like if we want to model high-res image generation. So currently, the way we deal with high-res generation is that we build this cascaded generation pipeline. So we have a base model working on small resolution image, and then we gradually expand it with some super resolution models, right? But if we want to build a single model on those high-res image directly, then the number of extra parameters we need is much larger than, for example, if you compare it with the super-res model that we use to upsample it. So that's evidence, I think, to support your claim that we need to build this process to be multi-resolution.
Yeah. Another small comment. I just think looks like we need to solve one stochastic PDE problems. So I just naively think that maybe multi-grid can also help to solve the PDE problem faster, even with a large DT. I mean, yeah.
Oh, you mean like develop like more advanced like
Yeah.
ODE
Can put it more forever. Yeah. And also, if you look at the problem in the whole time domain, right, then it's easy to use a parallel computing when we use multi-grid to solve the whole stochastic PDE.
Yeah, definitely. I feel that's definitely a very like active and exciting research field nowadays. And my hope is like we can combine those advanced samplers, for example, with the progressive distillation to combine the best of the two worlds.
Yeah. Thank you very much. Thanks.
Yeah, thank you so much for the nice talk, Ruiqi. I want to follow a little bit on like the distillation thing. So like you mentioned, after we do the distillation, it cannot be described as the score function anymore. And do you think if there is still any chance or any thoughts that this kind of like distilled model can also be used as a useful generative prior for solving like inverse problem, like what mentioned in like the previous talk we have seen?
Yeah, I feel like as long as your problem is relevant to, say, you want some guidance in the clean sample space, so that distilled model is still useful. For example, right now we are using some 2D diffusion model for 3D generation, so very similar to the inverse problem you mentioned. So we can actually run the sampling process with the distilled model towards clean sample, and then we design some loss functions in the clean sample space and backprop the gradients to the 3D model that we are interested in. Yeah, so I think it's relevant to what kind of information you want from this model. So if you want it to be like a critic in GAN model, like, right? So want the score to guide the generation of your complete data, then the score is still important. But if you want something, if you design your framework such that you can make use of this, the signal from the clean sample space and backprop the gradients from that space to your target complete data representation, that still should be useful.
Okay, thank you so much for sharing that. And another follow-up question is about the consistency model. It's also one kind of like distillation from the EDM, right? So how do you distinguish, or how do you give maybe comment on this kind of like maybe different distillation for the acceleration purpose?
Yeah, so basically consistent model, I think one advantage is that it doesn't have to be this progressive stages, right? So it's just like a single stage. But empirically, we found that the consistency model is less stable to train, but that's just my personal experience.
I see.
And I think one potential advantage of consistency model is that the whole formulation is still holds like after you get the trained model. It's not necessarily like progressive distillation. So after we have the distilled model, we can't train the model with the original diffusion model training objective, right? So it makes it less applicable when, for example, we want to do some fine-tuning of our model. For example, if we want to have we have a foundation model, of distilled foundation model, it's still not clear whether, like how we can directly adapt this distilled model to certain fine-tuned data. But for consistency model, because you can keep using the same objective they proposed in their framework to fine-tune on some like, downstream task or downstream data, I feel like that could be one potential advantage, but I haven't tried it yet.
I see. Thank you so much for sharing.
We have any other questions? All right. Well, thank you so much.
Thank you.